If you've ever seen a natural language to SQL system in a demo, it looks flawless. You type a simple question, the AI reads a perfectly organized database and instantly outputs the exact right query. Then you ship it to production. Suddenly, the AI is looking at thousands of columns spread across hundreds of tables, filled with years of undocumented tribal knowledge that lives entirely in your data engineers' heads. This chart shows how steeply accuracy falls as databases grow. Untidy academic schemas like the Spider 1.0 benchmark, AI hits a 91% success rate. But on the real-world enterprise databases in Spider 2.0, that success rate drops to roughly 21%. Faced with that much noise, the model starts making things up, inventing columns and returning silently incorrect data. The instinctual reaction is to assume the language model isn't smart enough. Teams will burn weeks trying to swap in a heavier, more expensive generation model to fix the logic. But the model is not the bottleneck. Generating SQL from natural language is a retrieval problem before it is a generation problem. The AI already knows how to write SQL. What it lacks is context. It is blind to your specific enterprise schema, your pre-aggregated shortcuts, and the unwritten rules of your data pipelines. To fix what the AI sees, you have to climb the architecture ladder, plain prompting, RAG, and GraphRAG. Moving up involves a direct trade-off, balancing your schema's complexity against the operational overhead required to maintain the system. You shouldn't upgrade just to have the latest infrastructure. Selecting the correct architecture requires diagnosing your specific failure symptoms before you pay the heavy maintenance tax of the next tier. The first rung is plain prompting. You take your entire database schema definition and drop it straight into the AI's prompt window. It requires no extra infrastructure. You write the prompt and you get immediate data generation. But this approach has a strict breaking point. Once your database crosses roughly 20 tables, or you introduce a second business domain into the mix, accuracy steadily degrades. At that scale, the dense prompt window collapses the signal-to-noise ratio. The AI fabricates column names, incorrectly mashing up mismatched table definitions. It also drops mandatory business filters, returning historically skewed data. When these errors appear, it is time to add RAG. When a bloated context window causes silent hallucinations, the solution is targeted data retrieval, not paying for a larger prompt window. That brings us to keyword RAG. This is the architectural sweet spot for most teams. It uses vector similarity search to find and retrieve only the handful of truly relevant columns based on the user's question. This targeted approach shrinks the prompt size by up to 50%. Because the AI only sees the verified columns you handed, column hallucinations are mathematically eliminated. RAG also lets you integrate a SQL validation loop. Before any query executes, the system checks the code and forces the inclusion of mandatory filters that the AI might have missed. However, keyword RAG has a severe blind spot. It operates entirely on surface-level text matching. Flat retrieval breaks down in multi-domain schemas. The term brand performance might mean clinical outcomes or commercial sales. Vector search cannot tell the difference. This creates forbidden join paths. The AI connects tables using foreign keys, bypassing required intermediate aggregations, returning completely wrong counts. Keyword RAG becomes useless when an AI must understand the unwritten, complex relationships between tables, rather than just matching up their definitions. To solve those structural ambiguities, you reach the top rung, GraphRAG. This heavyweight architecture natively models your entire schema as an interconnected relational network. Instead of relying on text similarities, this setup explicitly encodes the correct join paths and flags those forbidden anti-pattern edges directly into the database structure. The AI is fed perfect concept, first routing, forcing it down the minimum join tree required for accuracy, safely avoiding red line paths. This resolves multi-domain ambiguities and prevents related metrics from splitting, pulling them into a unified query cluster. But achieving this routing introduces a massive permanent operational burden on your engineering team. You now have to operate a distinct graph database, build dedicated data ingestion pipelines, and rigorously monitor your warehouse for schema drift so your graph doesn't go stale. GraphRAG is a necessary intervention for deeply complex schemas, but it is an expensive operational disaster if you deploy it before your data demands it. You should never choose your AI data architecture based on technological ambition. Let your verified failure symptoms dictate what you build. If you over-engineer early, you end up with brittle, highly complex systems that cost far too much bandwidth for your team to maintain. Looking at the scorecard matrix, we established the first tier. Teams managing single-domain databases under 20 tables must remain on plain prompting. For the second tier, the vast majority of data teams at standard enterprises should stop building at keyword RAG. It is the most efficient choice because semantic scoring and recovery loops solve almost all of those silent context failures without the overhead of maintaining a graph. The final tier is strictly constrained. Massive enterprises dealing with overlapping departmental keywords strictly require GraphRAG. At a massive scale, flat vector retrieval simply cannot perform the relational disambiguation required for accurate data routing. For those highly complex schemas, paying the heavy operational tax of GraphRAG is the only mathematical way to achieve zero hallucination trust in your queries. The practical rule here is direct. Never buy and maintain a graph database if all your system actually needs is a better vector search. A successful NL-to-SQL agent is not defined by deploying the most complex architecture. It is defined by accurately matching your retrieval infrastructure to the specific limitations of your data.